Right now, if I play forward, we don't have anything. So let's go to our sourcing and change what we have going on here. Right now we're at 100. Let's try something like 350. And then within this temperature, let's also do something that's somewhat close to this scale here. So I'm going to right click and say copy parameter. Let's paste a relative reference. So we'll reference the amount of fuel and we'll take maybe a fourth of whatever we're scaling the fuel by. So maybe times 0.25. And this will allow us to take our temperature values and put it to some sort of number that's about the same scale as what we have as fuel. We already talked about ignition temperature. That's how hot the temperature field needs to be. We might go back and adjust and play around with that in a little bit, but I want to talk about this fuel inefficiency right now. This fuel inefficiency is basically a way of drawing out your explosion. So the burn rate, it's burning fuel, right? And what this fuel inefficiency is saying is that with every single step, there is a certain percentage likelihood that no fuel is going to be consumed. So at point 2, that's saying there's a 20% chance that this burn isn't going to consume any fuel. So you might think, okay, well, that's kind of cool. If we set this to 1, we're now saying, okay, well, there's a 100% chance that this burn won't consume any fuel. And so, okay, well, if that's the case, then we shouldn't see anything blowing up because there's a 100% chance that that won't happen. But we do still have fuel that's burning. So it's not like this fuel inefficiency is going to not cause things to blow up. This fuel inefficiency is more about preserving the fuel over time. So here's a great example of fuel inefficiency. And what that is doing for us here is that it's allowing the fuel to randomize when it is fully consumed all the fuel. So if we just had burn rate, all the fuel would just stop at the same time because that burn rate is just giving it a fixed time. The fuel inefficiency would randomize the time in which different units of fuel get completely consumed. With this setup, because we set our operation to copy, it doesn't really matter. If we were adding in fuel and if fuel was allowed to stack its value over time, then this fuel inefficiency would cause a bigger effect. But again, because we're not doing that, here in this situation, fuel inefficiency isn't really doing anything for us. Let's set that to 0. And that's saying that at every single step, we are consuming a unit of fuel every single time. That's probably a little bit confusing in this scenario, but once you get to more violent explosions, this fuel inefficiency begins to really shine. Next up, we have this temperature output. And what this is saying is that in the areas where temperature and fuel combust, those areas are represented by burn. If we go to our smoke object and we go to this burn field right here, let's check that. And then let's also go to this burn tab and uncheck use smoke. And instead use a plane. So let's hide everything else for a second. And you can see that these areas, these bluish areas, contain the areas where that combustion is happening. This temperature output says these burn areas are allowed to add values to our temperature field, which is this. So we're doing that in burn, and we're also doing this in a field called heat. Heat represents our flames. So if I go to heat and check this on, we can see there is our flames, and we are also allowed to add to the temperature field with this. And this temperature output is saying how much temperature do you want to add with burn and with heat. What I like doing with this is I like going to our source temperature. Let's copy this value, and let's take about half of what we're sourcing in with this temperature output. So paste relative references divided by 2. And so that way we now have flames, we now have the areas where it's burning that can contribute towards the values in our temperature field. It's also worth mentioning that this temperature output is going to cause your flames to go higher in the air. This temperature that's pulling things vertically, again, is the main way that you would achieve this stretched out flame effect that you see right here. It's great for forest fires, and it's great for any huge fire where lots of gas around it has built up and has caused this really intense upward velocity. Let's check this multi-field. It's actually good to see what that looked like for a second. We might need to change our geometry and bring down our ember pit a little bit because I think things are getting choked out a little bit too much right now, just as a note as we go along here. But anyway, let's go to our gas released. And what this will do in practice is it'll basically take your flames and thicken them up. So it's the difference between having, let's say, a flame that's kind of really thick like that, and maybe thinner and wispy, kind of like this. And the way it does this is through something called divergence. Divergence is basically whenever we have hot air, and this is the way to think about it, we have an area right where things explode of hot air, and that hot air wants to go in all directions. So it's this expansion in all directions, and because of that, it's blowing everything outwards. So the way to think about this is that the areas that are combusting have these molecules that are really condensed in there. This is an area of divergence. Outside of those combustion areas, we have molecules that are less condensed. And so this is something that happens in the real world. High pressure wants to go where low pressure is and equalizes itself out. And so that's what the solver's trying to do here. It's trying to make this simulation divergence free by expanding in all directions. So that it's an expansion effect. Again, in practice, it'll thicken up your flames, and also it can cause your flames to shoot outwards towards the bottom like that. So if you want your flames to go in all directions, add more of this gas released. For this campfire, it doesn't make sense to have that at a very high value. Probably something more like 0.1 will make sense, or maybe 1 to just thicken it up a little bit. But right away, you'll see what I'm talking about with the flames. We're going to get a more wispy-like flame happening, like this. And the cool thing about the wispy flames is that they have a little bit more character, I'd say, sometimes. It's less defined by the velocity of things going in all direction, and it's going to be a bit more defined by the turbulence or by changes in our temperature field, which I think makes sense for a small fire like this. Anyway, if you didn't catch all that, don't worry. I'll come back to it eventually. Let's set this to 1 for right now. And in the next lesson, let's talk a little bit about what we have in these tabs and start messing around with our geometry. Like I said, we might need to actually move this around because it looks like we're choking down here with just not enough room for this thing to breathe. So we'll look into that as well as these settings in the next video.